So the materials program at LSU is based on the theme of discovering advanced materials. This is spread over a number of departments and a number of institutes across campus, taking advantage of the crystal growing capabilities we have in physics and astronomy and in chemistry, the ability to characterize those materials at our CAMD synchrotron and a number of departments, and the extensive computational facilities at our Center for Computation and Technology that enables us to simulate those materials to understand something about their properties. Jerry Spivey is a professor of chemical engineering and the director of our Energy Frontier Research Center. That center emphasizes catalysis research. Catalysis is important for all sorts of applications having to do with green energy.
A lot of the materials that we look at here at LSU are ones that are used in clean energy production, medical research, and everyday items that we rely on each day. Catalysis research focuses on the development of, in our case, solid catalysts that are used in the conversion of raw materials into clean fuels such as gasoline, into plastics and other structural materials. The EFRC has three thrusts: synthesis, characterization, and computation. Starting first with synthesis, what we try to do is to synthesize materials with every atom in a specific place, because how those atoms are arranged on a surface determine the type of reaction that's catalyzed. The characterization is the second part, and that tells us where the atoms that we've attempted to synthesize actually are. Putting every atom in a specific place in a catalyst is not easy. Using methods like X-ray adsorption that's carried out here at LSU's CAMD facility, we can determine whether the atoms that we've made in our actual material have been synthesized and whether they're actually located where we think they are. The last part of that is computation. So computation allows us to solve the fundamental equations that describe how materials behave and see if those match the properties that we observe experimentally.
Mark Jarrell is a member of our Center for Computation and Technology. He's a professor of physics. He's also a computational material scientist.
Computation and theory in material science are essential because you need to have that full gamut of techniques or methods of inquiry, going from synthesis to characterization to theory to computation and back to synthesis to characterization and so on. That's the way you accelerate materials discovery. In fact, that's the central goal of Materials Genome Initiative. CCT's new computer, SuperMind, is 470 nodes. It's 200 teraflops. It's a very powerful machine. What's special about it is that 50 of its nodes use GPUs to accelerate the calculation. One area of particular strength is in strongly correlated materials. And our synthesis group is really strong because we have three distinct groups that are doing synthesis of single crystals of strongly correlated electronic systems. David Young is a great example. In his lab, he uses a metallic flux growth to grow single crystals.
We actually have people growing crystals every day at LSU and doing the characterization here. All the things that we need to maintain a material science research program can be done at LSU. We're interested primarily in the electronic and magnetic properties of metals, semiconductors, superconductors, materials for energy research such as thermoelectrics and magnetocalorics.
John Dowling's a professor of physics and he's an expert in quantum computing.
Quantum computing is a new field of research that leapfrogs over classical computing power and allows us to solve mathematical problems that cannot be solved on any other type of machine. It's problematic in that the quantum computer hasn't been built yet, but that's something we're looking to try to do here at LSU.
One of the holy grails of quantum computing is to develop topological insulators. If we can actually develop a topological insulator, that really may go a long way toward actually trying to make a real quantum computer.
Topological insulators, one of the critical properties are the correlated spin states of the collections of the electrons in the topological insulator. Those correlated spin states can be used as the underlying qubits and the gates of the quantum computer. And because they're topologically protected from the environment, from the noise, we could also expect the quantum computer built from these materials to be protected from the environment and the noise and to run in an error-free fashion. Having multiple departments is a critical, important feature of the interdisciplinary nature of what we're doing here. We have physics, we have chemistry, we have computer science, all interacting, and the students are learning a little bit from each of those fields and contributing in a way that they wouldn't get if they were isolated in one department. The sort of broad material science, interdisciplinary cross-fertilization at LSU, I think, is unique.
There are more down-to-earth applications as well. So that, in fact, we have one company run by John Flake in our chemical engineering department that works on lithium-ion batteries. Companies like this bring money into the local economy. They also provide lots of good experience